Oh, snap. Hold on, y'all. I gotta change my name real quick. Gotta change the name. All right, there we go. What's up, guys? Kristen here, and welcome back to study sessions. This is the second study session. Okay, so look, here's what we gotta do. First off, I gotta send gotta share this meeting link. Oh, cheese, cheese freak. Hold up, share the meeting link. Uh, Hold on one second, y'all. I'm gonna start sharing the stream again. Hold up a second. Okay, we're ready for. I think we're ready for this. Um, let me just double check on the live. Let me double check the live stream. Make sure it's still going. Okay. Um, so okay, there we go. Yeah, had to go back and. All right, cool. Yeah, so we're back. We're back. I think. Are we back? Yes, now we're back. Okay, cool. My live stream is a little bit lagging a tiny bit behind, but I hope y'all can hear me well. I'm not gonna. I'm gonna be honest with y'all. You may, if you put something in the chat, it may or may not get seen. I can't guarantee it, but today we're just boy, God, man, open the dang your thing. Jeez. So we got some information from our great professor, Dr. Bosshard. Wonderful man, wonderful man. He's very knowledgeable, very good at what he does. For this Smith chart problem, you find the radius on the Smith chart, and you move to the left from the center to the left. Now, when you move from the center to the left, that allows you to line up with the Smith chart. If you look back to this right here, so the Smith chart has a bunch of geez. The Smith chart has a bunch of these things right here, these markers. So from the center line, you find the radius out to the next point, and then that gives you your VSWR, your voltage standing wave ratio. So let us continue. The next question I had asked was find I think this should be divided by 2 pi. Find Z naught, L, and C of a coaxial cable. So we use these equations here. We have mu. Oh, goodness, y'all can't see this. Um, by the way, my friend Alex may be joining us. He may not have his camera on. I don't know. Oh, geez, that's up to him whether or not he wants to do that or not. Um, but I use the values of 12.2 millimeters and 4 millimeters. So you're going to take your mu value. That would be mu equals mu naught times mu r. For coaxial cables, mu r is usually not 1. So we'll say mu r equals, let's just say 4 as well. So you'll take your mu r value and you multiply that by your your other stuff. But you really only need to. So the first thing we should do is find what L is. So we know as given, um, L is mu over 2 pi times the natural log of big D over D. So if we take the natural log of 12.2, well, this is assuming meters, so we'd have to do 0.0012, no, 0.122, yes. And then we divide that by 0.004. We have natural log equals 1.115, and then we do mu. So I have it saved in my calculator as u. So mu times 4, and then you divide that by 2 pi. Make sure you're using parentheses, otherwise you'll get an incorrect answer. So if you notice here, I don't know how well the reflection or glare is going to be, but if you notice there, I have parentheses around 2 pi. So I do that, and then I multiply that by that value of I multiply that by the value ln d over d, and then that gives me 0.89 microhenries. All right, and then we do the same thing, except we use epsilon. Epsilon, if you remember from our last stream or earlier in the class in the year, epsilon naught times epsilon r equals epsilon. We'll go ahead and say that epsilon r, we'll give epsilon r as a 12. We'll just say epsilon r is 12 this time. So we'll say epsilon r equals 12. Um, so we now have 8.85 times 10 to the negative 12 times 12. So then we'll do 2 pi times epsilon. I have that also saved as E, I believe. Let me make sure. Yes. So we multiply that by 12 times 2 pi. And then we divide that by that same value one of L natural log of 1 over D of D over D. So we divide that by that, and we get that equal to 59, yeah, 59.84 picofarads. And so then 1, 2, 1, 2, 11. Um, if you're ever unsure, you can always put the number in again and put to the negative 12. Oh, um, excuse me, not 59, it's 598. 598.4 picofarads. So with these two values, now we can calculate Z naught. And Z naught is this equation here shown. So we take the natural log of D over D. I didn't put parentheses around it, but I should have. So this should have parentheses around it. So we take that 1.1 whatever value, and we divide that by 2 pi, and then we multiply that number by the square root of L over C. So we take that 0.89 microhenry So let me go ahead and put this in the square root a second. And then you divide that by your capacitance per length, per unit length. Then you multiply that by, and you get Z naught for this line. If I'm not wrong, should equal 6.853 ohms, if I've done it correctly. Someone who's better at this than me, y'all should go back and check it, double check, leave in the comments if I'm wrong. I love to learn. I'd love to make sure I do it right. Somebody asked during our review how to find the open circuit, if you have an open circuit transmission line to implement a 22 picofarad capacitor with a frequency of 128 megahertz. You want to find lambda or find length of the line in centimeters, and its velocity factor is 67%. So the first thing you have to do is you need to find the impedance of the capacitor, and that ends up being negative 56.52 J. And Zn has its formula. I did not write it down properly, but I do think I have a picture of that. Goodness gracious, like, jeez, that was a lot of stuff. Oh, I should send a message to my friend now instead of. Oh, I was just thinking about you, man. I was just about to send you a message. Um, by the way, this is live. I hope you're okay with that. I don't know if you've joined the audio yet or not, but
Yeah. We're chilling.
um, so yeah, I'm just going over some of the things that we went over. Do you happen to remember the um the equation for Zn?
For Zian, let me pull up my notes and stuff. Uh, for transmission line or
Yes, I believe for a transmission line because this is a transmission line problem. I believe he gives it to us on the formula sheet, right?
uh, he gives us a Zian. He
It's
gives
like Zn
us
equals Z
several
naught,
Zians. Z naught squared over Z2.
not that one. It's like Zn equals Z naught time Z naught
Oh,
plus
Z2 plus
J.
J Z naught tangent beta L over Z naught plus J Z2 tangent beta L.
Okay, yeah. So could you repeat that slow for me real quick?
Yeah. So it's
So
Zn is equal to Z naught times Z2 plus J Z naught
wait,
tangent
hold
beta
up.
L.
Z naught times Z2 plus J Z naught, right?
Yeah, J Z naught tangent beta L. And then that's over Z naught plus J Z2 and then tangent beta L as well. So it's basically just the same equation that we use for finding gamma, except using the impedances and then adding in or it's like the same idea behind gamma.
Okay. So um would you like to work this problem or you want me to work it and change something a little bit? It's up to you. This is just a study.
Go ahead and work it. I'll follow along
Okay,
unless
so
you already did.
so the one we worked in class was an open circuit. So I'm going to change this to a short circuit. The only thing that really changes with a short circuit is that you just use a quarter wavelength shorter, essentially.
Yeah.
Um, so we find our Zn by taking Z naught. We know Z naught is a 50 ohm transmission line, so we say 50 ohms equals Z naught And then we know from our capacitor value, 22 picofarads, if you find the reactance of that, which is 1 over j omega c, that equals 50, excuse me, not that, it equals negative 56.52 j. Do you mind double checking me on that, making sure I got that right?
Yeah, I gotcha. 1 over j omega c.
And then your frequency is 128 megahertz.
128. Yeah.
128, yes. This problem was given to us by a nice young woman in the classroom. Um, she was sitting next to me to my left. She seems very bright, probably a lot smarter than I am, but it was a great question. I'm glad she asked it.
I got something different. So if it's 1 over j, oh wait, I just did frequency instead of omega.
Yeah, you gotta remember the 2 pi.
Yeah, always gets me.
Yeah, this is why it's good. It shows that like even as engineers, we'll sometimes make mistakes, but that's why you should always have two engineers on a problem.
I still got something different after that though.
Okay, let me see if I did it incorrectly. So you have 22
Are you in
picofarads.
radians or degrees?
It shouldn't matter because this is just flat values. 22 picofarads.
Yeah, so 1 over
I
22 times 10 to the negative 9.
dude, that's to the -6.
Pico?
Oh wait, no, pico is to the -12.
Oh, yeah, yeah, yeah.
That times two
That would
pi.
be my mistake. Yeah, negative 56.51 here. Man,
Okay, cool. Um, so with that value, now we can plug those two in for z2 and z naught. So rewriting this problem, we have this was actually what took up so much of my time on the second exam, because I could not write the right equation for 5 minutes straight. So you have 50 multiplied by 56, well, negative 56.52 j plus j 50 tangent beta L, and then you divide that by 50 plus, well, it would become negative. I believe the J's would cancel and actually make it a plus anyway, because if you have J is just the value that for anyone who's watching, that doesn't know, J is just the value we recognize as -1, the square root of -1. The square root of -1 times the square root of -1 is is -1, and then yeah, so and then since it's already a negative J, like it's already a negative value, that negative times the negative will end up making it a positive. So you would just have 56.52 tangent beta L. I think that's right. Um, so if you do 50, well, if you break this down, how did he break it down? Um, I forgot what ZN was.
what's Zn? The formula for Zn or just the value?
I forgot what the value of it was.
Isn't it just a 50 if it's a 50 on turns?
Well, that would be Z naught. Hmm. Let me see. Let me see. Can I do this any differently? I know it breaks down to where you end up getting um, basically tangent, inverse tangent of 50 over 56 equals beta L. Oh wait, no, there's no input impedance. It's just you're just trying to match the impedance. So there's no input. I don't think there's an input at least. Because if you're trying to match it, then it would net to zero. Or I guess still ZN. Oh, you're right. It would be 50 because that's the only way you could do it algebraically. Because 50 divided by 50 would be 1. And then to multiply that by the other values, like that's the only way you'd be able to actually get it to work around. So you have basically 50 equals ZL plus J Z naught tan beta L over Z naught plus J Z2 tan beta L. You multiply those two together. You multiply both sides, and then that gives you 50 times 50 plus J tan beta L equals 50 or equals Z2 plus J 50 tan beta L. Um, um, essentially, the math just like I don't really understand all the way of how to do the whole math. Oh, wait, hold up, I needed that. But essentially, in this specific case, Zn equals negative J50 times cotangent beta L, and that ends up, and that's because you'll end up having Zn equals minus J50 times 1 over tangent beta L. That's just that's just how the math ends up working out in this case. It should be pretty obvious. It shouldn't be as messy in a sense. And I think he has the solutions to this on his exam. I think this is an exam problem or it's a homework problem. I can't remember which one. Um, but anyway, once you get down to the point where you have just beta L by itself, or you're just trying to solve for beta L, which I guess we could also argue for where we were in in the previous point of the example. You just need to do omega over the speed of light times the velocity factor. That comes out to about 4.001. And then if you do, how do we get 0.7247? Ah, yes. So if you do the inverse tangent, um, basically, if you solve this to equal beta L, you'll eventually have something that equals inverse tangent of pretty much 50 over 56. So I think I'm working it out right over here. Then you divide this by negative 56.52. That gives you tangent beta L equals, oh, that should be J. And then you do inverse tangent, and that solves all your problems. So then you do beta L equals, and then when you do the inverse tangent of 56 over or 50 over 56, you end up getting this L value, or this 4 rad L equals 70.7247. And then you can find that L is 18.1 centimeters up. So that's pretty much how that one's done. Um, a lot of the complex math, not the greatest at it, but I hope it made enough sense. Let's see the problem. So this impedance matching, this one can be done on a Smith chart. If you enter the Smith chart with 76 divided by 50, and then you have 14 divided by 50, you'd be at the I'm not doing this on the screen because it's hard to do Smith charts without a straight edge and or a compass. So if you need that, you should probably pull out the compass now. So where we're starting at would be so the first thing I did was enter the Smith chart, and to enter a Smith chart, you need to normalize the values. And that means divide by Z naught. Alex, do you have any Smith charts nearby?
I don't.
Man, I'm prepared.
Yeah, for real.
So, um, with the values that I found at 1.5, let's see, 1.52 and 0.28. So that's a minus 0.28, and that's 1.52. So I'm going to go to the 1.5 line and then go down just a hair. And then it was at 0.28. So that's right about the 0.3 line, just barely off from there. You're going to just have to trust that I'm doing this right. For the most part, I will explain as I go, but I can't really show everybody the thing at like while I do it. So now we take a compass, put it at the right spot, and then you just draw your circle. I don't have a flat enough surface to draw this on. So excuse me while I give y'all the wonderful side of my face. Close enough. Good enough circle. We'll call it a good enough circle. Um, I mean, I guess I should draw an illustrator that adds accuracy to your measurements. The more accurate your circle is, the more accurate you'll be. It's like an exact science, but it's not an exact science. Um, it's kind of left up to random chance at times. Okay, that's what. Okay, cool. So now, um, in order to match the load, we're probably going to want to use impedance. So after we've entered the Smith chart, we're gonna flip over to the other side of the circle and make that an impedance. So you're going to take your straight edge, line it up with the point you made, and then draw a straight line to the other side of the circle. That is now your impedance. You're in impedance mode. Now what you need to do is you need to find where your circle intersects with the one circle. You find the first point at which it intersects with the one circle, and that's always going you're always going clockwise. Don't go counterclockwise, always go clockwise. That seems to be right about here. Yeah, that seems to be right about here. So then we're going to take our straight edge and draw from the edge of the circle where we're crossing we're going to draw from the center to the edge where we've made our dot, go all the way down across. And then we're going to take another line and we're going to do the same thing at the point where it crosses over the one line. So as a rough general estimate, we'll need, so you're going to be reading, I hope y'all can see this. You're going to be reading these top values where it says towards generator. You're going to read those values. So you have 0. I think that's 0.03. Yeah, we'll say 0.03. And then where it crosses over is 0.142. So you do 0.142 minus 0.03. You get your width of 0.142 minus 0.3. You get 0.112 lambda. So that is the dot. Let me write that down for y'all. Oh my goodness, I dropped my pen. By the way, this is not sponsored, but shout out to the makers of this pen. Shout out to them. What company is this? I don't even know what company this is. Let me put y'all on real quick. I think this is I think their company's called Digiroot. Digiroot, not sponsored, but shout out to them. This pen lasts 9 hours on a full charge, and it was only like $10, maybe 15. So if you got an iPad and you're like, I'm not an artist and I don't need to buy myself an Apple Pencil that's like $200, this one right here, 9 hours of battery life, charges in less than 15 minutes. I kid you not. I plugged this in for 3 seconds. I'm basically full. It's more like a minute and a half, but y'all get the gist. Anyway, wishful thinking, sponsorship brand aside. Um, so the value we got was 0.112 lambda. Um, so now we need to, so that's the length of D1. So if we were to draw this as a picture, let me draw y'all a picture. Even though I can't draw, I'm not an artist. What the that is not. Alex, do you know how to turn off the iPad trying to autocorrect my stuff?
If you're using OneNote, there should be if you go to settings, I think it is,
Oh, that's what I accidentally hit. I accidentally hit
or like
that
auto
box next to
shape.
the shape. I
Yeah.
accidentally hit the box next to the shapes. Um, I was wondering why it was like messing me up. I was like, bro, I know my drawings suck, but my letters they be looking right until y'all go and mess them up. So this is the length of D1. Sounding like Mike Tyson for a second. This is the length of D1, and then we want to connect a line. We're gonna connect a short this time because after talking with Dr. Bossard, in most situations you'll probably end up using a short because it just ends up being a better implementation of the wire. So we want to match that load to we want to match that impedance to 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 50. So right now we have 1 plus um what is that? 1 plus like point 0.49J. So we need minus 49J. So we need our emitted stub to equal minus 0.49J. Oh, y'all can't see that. There we go. There y'all go. So in order to do that, you just find minus 0.49J on the Smith chart. Wow, shocker, right? Who could have seen that coming? Is that right? Yeah. So now we take our straight edge. We go right back through that line and find that lambda value. That gives us 0.345 or 346, something like that. So then we do the distance from 0.346 to 0.14. And that gives us a lambda of 0.206 lambda. And then you can use that to match it to any load. So no matter what the frequency is, you can find the wavelength. So if you have like 100 megahertz, you can find the wavelengths and then multiply that by that. If you have like 20 megahertz, you could do it. Matches anything. So Alex, let's see if you got this next one. But I'm changing the numbers.
All right.
4.9 meters. And operating at what's your favorite number, Alex?
Let's go with 700.
Act like the 2D squared is not there. Well, actually, you kind of need it. I think you said this is on the formula sheet.
It is. So RFF is the far field distance. So you would do first you have to find lambda, which is c over frequency, which is 3 times 8 over 7 megahertz. So 3 times 58 over 700 times 10 to the 6th. That'll give you 0.428571. And then since it's 2 times distance squared over lambda, you just plug in the distance. So you have 2 times 4.9, which is in meters. If it wasn't, you would have to convert it either 2 meters or just have your final answer in whatever distance you had originally. So 2 times 4.9 squared over that 0.428571. And then that'll give you a final distance of 112.047 meters. For the if I could do math, which I'm very questionable sometimes.
Well, that's why I'm going back through and working the problem little by little. That's what you got, 112.04 meters.
Yep.
Wonderful. You see, we're cooking with gas now. Cooking with gas. I didn't do any of the antenna homework. Not by choice because I was studying. It was because I was studying everything up to antennas and kind of didn't get to it.
Yeah, I feel pretty comfortable with a lot of the antenna stuff because it's relatively straightforward, right? I
I
mean,
think I understand it. I just don't know all the formulas for it, but I think he gives us most of them.
yeah.
So, do you know how to do this one? An isotropic antenna radiates at 153 watts. Find its efficiency and power density at a distance of 7 kilometers.
Okay, so if it's 153 watts, its efficiency would just be that over 4 pi, right? So 153 over 4 pi would give you
12.1.
12.1754, and that's in watts per SR, right? What I don't remember.
Watts per seradians or something like
Yeah,
that.
steradians, yeah. And then after that, since it's just 7 kilometers, if you're trying to find its power, is it? Would that be the if no power density is the no wait that's radiation intensity. What I just saw. Power
Uh,
density is the radiation density over the distance. So 153 or the 12.1754, you do that divided by this.
Divided by 7 kilometers.
Yeah, and that gives you its power density, which would be 0.001739. So 1.739 milliwatts per steradian. And its efficiency is going to be uh, what 153 watts times what is the formula for the efficiency?
Oh, I just now realized that would have been a big L if my stream just shut down because my laptop died.
That would not be.
I also might need to like get some cooling or something for my thing because it's getting hot.
Mm.
Maybe upgrade my fans or something. I don't know.
Yeah, I have a little like cooling stand for my laptop. It sounds like a jet sometimes. See if I can find one of the.
Oh yeah, the Bengals won one Monday night. Way to go, Jake Browning. Your pass percentage is higher than all of my grades. I'm not really ashamed of that because 83% or 86%. That's pretty darn good for a passer. Did you find the equation?
So yeah, we did the first part of it right. For solving the power density, the 1.739 watts per steradian is correct. I have to find the efficiency. Efficiency is the power radiated over power. Is PT power transmitted or is it power?
Power transmitted. Yeah, PT's power transmitted.
Oh, PT is what we have. The power radiated is No, power radiated is 153 divided by the power transmitted.
Oh, we need to use the directivity. So we need to find the loss in dB. Like that G value, we need to find G.
Yeah, but it's the same thing as the P rad over PT though. So I'm trying to figure out like is we're given the power radiated, which is 100 watts, right?
Yes.
So how do we solve for the power transmitted? I feel like that'd be faster than
Um, did I give power transmit? I'm trying to figure out if I actually gave power transmitted and not power radiated.
that's what I'm wondering as well.
Because this is the same. It's a very similar problem to question 8 or the homework 8 questions.
Yeah.
I'm gonna check the chat, see if somebody left an answer in the chat. Don't start a fire. Um, well, we might already be at that point. I'm gonna keep it a buck with you. That's all the chat says. Don't start a fire.
I mean, I don't know if we have enough information to solve it.
Let's
Is it
see.
we have to be given, I guess.
Okay, so that this is based off of question two. All it asks for is what's the radiation intensity and what is the power density. So we found radiation intensity. That's the 12.74, right?
Yeah. And then the power density is uh the 0 point or no, 1.739 watts.
Okay, so with the help from the homework, um, so now we should be able to find the isotropic radiation intensity from this. Okay, okay, hold on just a second, y'all.
The isotropic radiation intensity would be the 12.174, would it not?
Got a medical phone call. Can't let y'all know what's up with the medicine. You know what I'm saying? You know, HIPAA violations and all that. But what were you saying about isotropic radiation?
Isn't the isotropic radiation intensity the 12.1754? Like, what would the difference be between the isotropic and just regular radiation intensity?
Um, did he notate a difference?
I don't think so.
Okay, well, I guess we have that. So what is the measured radiation intensity in the direction of the main lobe? So assume that the 153 watts is in the main lobe.
So wouldn't that just be I guess if we're assuming that the radius or little r is the distance, that's what r squared times um, the power density, right?
Yeah,
So
yeah.
it'd be 4,000 squared times the 1.739 milliwatts. Oh, four, or
Wait,
no,
where'd
four,
you get
or
4,000?
not 4,000, 7,000.
Oh yeah, 7,000. So yeah, I just read that as well. So you'd put in
Yeah.
uh what's the symbol for that? Is it mu naught or something? Or G naught?
Uh, for which one? The power density or
The one we just saw for.
uh, isn't it just U max? What it says, or that's what it says on the homework notes for the problem that's like that.
So it says 7,000 squared times the power density.
Yes.
That gives us 85,227.
Yeah. Seems large, but I think given our numbers, that's right.
And then the directivity in decibels. So directivity 4 pi times 4 pi times U max. Is that divided by something?
U max divided by U ISO is the directivity. But for
No, I'm
converting
saying
it,
for gain. For
oh,
gain.
uh,
That's divided by Pn, right?
I'm not sure.
Because looking at the thing that says for gain, um, oh, antenna efficiency, P rad over Pn. So that's how you find efficiency. For gain, u you have 4 pi. You basically have u theta phi, which is just 4 pi u max divided by Pn over 4 pi. So you have, I guess you'd end up having the 4 pi gets multiplied in because you multiply by reciprocal. So you have 4 pi u max over Pn. And then I guess you could do 10 log of that. Or is it 20 log? Is it 10 log or 20 log?
It's 10 log.
So that gives a loss in dB of 38.4, which I think is reasonable.
That's what I got as well.
That's that is the loss, right? Like that's loss.
Uh, is directivity always lost?
I forgot what the term was that he used. Directivity, yes, directivity. Unless I'm using the wrong thing.
No, it is directivity. I just don't know if it's. I guess it could be quantified as loss in that direction.
Wait, directivity is in dB. So U max over U naught. And U naught is P rad over 4 pi. So 3 divided by. Oh, wait, so that's not correct. So So that over that. So how did you say we find Umax?
Umax is the what we saw for earlier. So it's the
85,000.
yeah.
Okay, so the
I
directivity is actually 7,000 for the most part, and then in dB,
I still got 38.45
yeah, okay.
dB. So you probably still solved it the correct way. It's just a matter of different terms.
Okay, cool. So that's how you find isotropic antennas stuff. Um, do you want to do a microstrip design problem?
I'm done.
All right, I'm gonna let you create it so that way we can have like some unique numbers.
All right. Design a microstrip patch antenna, or just like microstrip or like microstrip antenna.
We can do both.
Because I'm also like looking at the homework in
Well, yeah, I came
today's.
up with a microstrip patch antenna problem.
All right.
So this for the microstrip patch. Um, that was in our ground plates notes, right?
I think so. The microstrip design equations, it's like right after Smith charts.
No, I was saying the antenna patch
Oh,
or the
antenna
patch
patch.
antenna.
Yeah. It was the notes from November 30th.
Yep, I'm looking at them now. So I guess it would normally give us height, right?
Um,
Because looking at the equation, it doesn't look like we have anything we could solve for height, at least not easily.
it would have to give us either width or height, I believe.
Well, I'm just saying, looking at the equation, it doesn't look like we can find h from anything. Unless you see something different. Might email him tomorrow or something and ask him how we would find height if we needed it.
You're looking at the delta L over H, right?
Yeah. So we don't have like
Yeah,
we don't.
yeah, we can't solve for H unless we're given everything else. And like literally the problem is just do like delta L times or delta L over the zero, like the rest of that equation, which I mean at that point we'd already have H.
Okay,
Or
so
we'd solve for H.
we're gonna revise our question Sorry about that, y'all. I thought we would be able to solve for H like a real microstrip transmission line, but apparently not. Okay, so cool. 3.1 meters. So we know that delta L over H equals, that should be on the formula sheet, right? Because it's like a very
Yeah, it
specific.
is.
Are you looking at the formula sheet now?
Yeah, it's delta O over H is equal to 0.412 um,
I'm writing it
times,
down. It just might take a minute to go.
yeah,
Go
uh,
ahead.
so times E ref plus 0.3 times W over H plus 0.264. And then that's over E ref minus 0.258 times
Oh, you're
W.
saying epsilon. My bad.
Yeah.
I'm writing E.
Sorry, I should have said
You're good.
epsilon.
Epsilon R over what? On the bottom, epsilon R what?
Epsilon ref REFF minus 0.258 and then times W over H plus 0.8.
Okay. Does it look right on the screen when everything pops up? Just let me know if I need to print size anything or I want to make sure that any viewers that are watching get the exact answer.
I'm still waiting for it to. Oh. Yeah, you just might want to so the top one do
Mhm.
epsilon ref plus 0.3 and then parentheses around that and then it's times the parentheses W over H plus 0.264. Yeah.
Cool.
And then on the bottom, do a parentheses around the epsilon ref and the 0.158.
I think that works.
Yeah.
Or is it this first? Like, is it,
It's epsilon ref minus the 0.158 and then it's yeah.
and does the W over H, does that need to be in parentheses as well? The W over H plus 0.08? I'm just
Yeah.
not looking at the formula sheet right now, so I'm not sure.
Yeah. It does.
Okay, cool. So it looks just like this on the formula sheet.
If you put another like closed parentheses after the 0.3 on top, then yeah. Yep. That's it.
Okay. Woo. Okay, so after you do this, you can find epsilon effective with L plus 2 delta L. Is that correct?
Yes. Or that's yeah, L effective or like
And then you can find W with L over 2 FR.
I have it as C over 2 FR.
Okay, yeah. I may have written it too quickly to get legible writing. So W equals C over 2 FR. Why must you do this to me every freaking time? Come on, game. Come on, iPad. You're supposed to be the thing of the future. Imagine being the thing of the future and then malfunctioning. Like that's kind of embarrassing. Um,
The C over 2FR, and then it's times the square root of
square root of
2
two
over epsilon R
epsilon
plus
r
1.
plus one.
Yeah.
Okay, cool. So epsilon r is given as 1.7. What is FR? Like resonant frequency?
I'm assuming so.
Did he give us one of those on the homework problem?
Let me look. Resonant frequency was not given, but it's a frequency, an operating frequency is given.
Yeah, I saw 6 gigahertz.
Yeah.
Did I forget to give y'all a frequency? Oh, 3 gigahertz, operating at 3 gigahertz. Do you have it written down as FR as on yours as well?
I have it as FR, but it might just be frequency. Like, I don't know.
Like operating frequency?
Yeah.
Maybe it's already assumed to be its resonating frequency.
Yeah.
All right. I mean, I guess. Goodness gracious. Um, so I guess now we can solve this. I think it'd be best if we both solve half of it. So I'll solve the first half with W and epsilon, and then plug those numbers in where they need to go, and then you can solve the what's it called? The L over H.
Okay.
I'm not sure if he gave us how to solve for delta L though.
I mean, we just do whatever we got for the formula times H. And that gives us delta L.
You see times 2FR. Okay, cool. So the epsilon R in the bottom of the square root, that's just epsilon R, right? It's not epsilon.
Um, no, it's epsilon R effective, which is the epsilon R plus 1 over 2 plus epsilon R minus 1 over 2 times 1 plus 12 H over W to the square root of that.
Goodness.
Yeah.
Okay. Because I think I wrote that down wrong. Oh, I know. It is effective, epsilon effective. What was that equation for the dielectric constant? Because that's a That's on the formula sheet as well, isn't it?
Uh, what is,
Epsilon effective.
yeah, epsilon R effective or just epsilon effective?
I think it would be epsilon effective because that's the one that's on the that's the one underneath the square root in the two times or the c over two fr, right?
It's just epsilon R.
Oh, that was just epsilon r.
Yeah. When solving for width, right?
Oh, yes. Okay, cool. Now I was thinking I needed more than I did. So the first step after making sure you have all your values that you should have is take c, which is typically the speed of light. So you have c over 2 times 3 gigahertz because 3 gigahertz is given. Then you multiply that by 2 over 2.7 if you just do the mental math of 1.7 plus 2. Just letting the thing catch up. Giving it a second. There we go. Okay, wonderful. So after you do that, you just plug in your values. So you have oh yeah, Alex, do you have your numbers like the constants like epsilon naught, mu naught, and c as like values already saved in your calculator?
I don't.
Do it, man. It's gonna save you some time. You because you know how to do the store function, right?
I should look it up though.
You have an 84, right? A TI 84.
I have a Inspire CX.
Do you see anything that says STO?
Oh,
If you see something that says STO, that's usually store. Like it's STO with an arrow.
all right, I found it.
So then you can do then you can just do the value and then hit store and then you click on any like you can click on any alpha key. So like you get store and then alpha something and then you can store the value into that
Gotcha.
letter. I hope that made sense. Like I think I skipped one step. You have to have the number and then hit store. So it's like 8.85 times 10 to the negative 12th. And then you hit store and then you put like E for epsilon or something like that.
Yeah.
And then to check to make sure it went through, you can just hit that letter and hit enter and it'll give you the value that was there.
Okay.
So C over 2 gig or 6 gigahertz, that gives me 0.5. Then I multiply that by the square root of 2 divided by 2.7. That gives me 0. So that gives me W equals 43.0 millimeters. So then um, we're given height. So now we can, so you said we can solve for delta L using the top equation, plugging everything in, right? Wait, no, we need
Uh,
to,
we could solve for it as long as we have H already.
we do have H. H is
Yeah.
3.1, but we don't have epsilon R effective.
As long as you have W, you could solve for epsilon R effective.
Okay, how do you do that? Like what's the equation for that?
Um, so it's epsilon r plus 1 over 2 plus epsilon r minus 1 over 2, and then times the square root of 1 plus 12 h over w.
Hold on, I'm gonna have to write that over here. So you said epsilon r plus 1 over 2, epsilon r minus 1 over 2. Those are added together, then that's multiplied by 12 over
1 plus
hw.
12, yeah. 1 plus 12 h over w, the square root of 1 plus 12 h over w, sorry.
Okay, it should show up in just like that.
Yes.
Okay, cool. So to make it easier on Alex, gonna gonna give him epsilon ref. So we do 2.7 over 2, then then I guess 0.7 over 2. Nope. Yeah, 0.7 over 2. And then you do square root 1 plus 0.0031 and 0.00 or 0.043. Yeah. Wait, no. Almost forgot my times 12. Okay, cool. Then 12 times that. So then you do that, multiply by that. Yes, that. And then plus 1.35. So your ER8, your epsilon R effective should be 1.828. Is that what you got when you plugged in the same values?
Uh,
I'm not trying to make you solve it twice. I just want to make sure that I give you the right number before we move on.
I'll double check it real quick.
Crimson, one of the viewers says he finds the study streams interesting. Um, then you might have a future in electrical engineering or something like that. You might like electrical engineering. So I forgot. I don't know if you said what you were doing for college or uh, when you graduate, but take a look at electrical engineering. You might like it.
Yeah, 1.828 is what I got as well.
Sweet, sweet.
And
So
then
now
plugging that into the big equation, I got 0.538.
that's lambda over h or
Yeah,
delta L
delta
over
L
h.
over H. So if we just multiply that by H, that'll give us delta L. So
What did you say for that value?
0.538.
Okay. And then if you multiply that by, yeah, like he was saying, if you multiply that by h, so
It's 0.001668. So I guess 1.668 millimeters is our delta L.
yep, so delta L. And then the H and L, that was because I thought we were able to find H, I think. But we're not able to find H. I kind of wish he would grade the homework 8. Like if you did it and turned it in, I kind of wish he would grade it, but there's also a lot of stuff we need to do.
Yeah.
So it says find the width of a microstrip feed line on this substrate. So let me see. That goes back into design equations, right?
Yeah, or using if you're looking at question 8A, it's what we just did. But to find the actual L value, since delta L is different.
No, I was saying
Uh
the width of the microstrip lines.
oh, yeah. So that's
That
back to
all right. You mind pulling those equations up and reading them off so I can write them down real quick?
let me find them real quick.
Also, I just want to give a quick shout out to everybody who watches these streams in general, especially the study ones. I appreciate you being here. It means a lot. I hope you're learning something. But thanks for tuning in. Oh, he said he was doing astrophysics, maybe minor in electrical engineering. Um,
We have our W and H values already, right?
we need to find another W value because this is a different W. We have
Okay.
8.
Um,
I know it's W over H equals something.
well, remember these are the ones with like the three different equations. So for W over H is less than 1, which is a high impedance region, we have a certain set. For it greater than or equal to 1, it's the low impedance region, which is a separate set. And then if it's less than 2 or greater than or equal to 2, then W over H is equal to something. So don't remember how to gauge. I mean, I guess we can look at the
I mean, we could assume that it's greater than 1, like a high impedance region.
yeah. Remember we have that little chart there where it gives us our Z naught in ohms, and then we have to line that up with the W over H
Oh
value,
yeah, yeah.
and then we
Let
have
me
the
see if I can
lines.
let me see
I
if I can
I,
pull it up real quick.
I have it
You
pulled
got
up.
oh to educate the other people on the stream, I'm gonna let you be able to share and take
All right.
over. So if you want to go ahead and hit that and show off the beautiful chart. I asked Dr. Bosshart if he would be kind enough to give us the chart. I think he said something to the effect of if he's in the Christmas spirit, he'll give it to us. So I think it's on the test if we need it.
I don't know if you can see if it's just my background or if it's
We can see the chart.
okay.
I think we can see
So
your whole OneNote for the most part,
all right. So here's the chart. So if our Z naught is 50 ohms, I guess we just look
which
at
it
where
is.
so 50 ohms, and then FWH is this is where W over H would be 1.
Keep in mind that this chart is on a logarithmic scale, so it's not evenly spaced, or it appears to not be evenly spaced, but it's a logarithmic scale. Um, and our epsilon R value is 1.7.
So
So if you look at if you're able to find a chart like this, I should put that let's put that link in the chat. Yeah, I'm gonna go put that link in the chat real quick. But do your thing, Alex. I trust you to explain it well.
I don't know if I can explain. um,
I believe in you. You got it. The best way to learn is to teach somebody else.
that is true.
So teach us, Alex. I'm just trying to make sure I go and grab the right the chart
What were we using as our H value?
for H.
Yeah, our new H. Is it 2 millimeters? Or
H was 3.1 millimeters.
you know, um, so this is where we go for H is 1, and only so Chris, how do you remember how to determine which, like, I guess, line to use for the W over H value?
Yes, I do. Let me come back to Zoom to help you out a little bit. So, oh, that is me zooming. Okay. So when you look at the transmission line, or when you look at the impedance value, that tells you where you're looking for the intersection point. And at that specific intersection point, it tells you um what value you're going to be following. So I actually might go ahead and try and share my screen real quick.
Yeah. The only problem that I was seeing is that there are like 4 intersection points. So
Well, yes. So streamception. Okay, so let me. Oh, geez, come on now, Max. Okay, so if you look over here in this region here, you can see that the different line colors are different.
yeah, those are the epsilon R values.
Yeah, so with our epsilon R being 1.7, we're going to be following pretty closely, um, slightly above this blue line. So at 50 ohms, where it intersects at this blue line is right about here. Yeah, right about here. So we know that our epsilon R value where we have it set, W over H is definitely greater than 1. So it's definitely greater than 1, no doubt about it.
Yeah. And then so are we doing a design problem or an analysis?
We're doing the design part first, so we need to figure out
Okay.
what the width of the load line is, or the lead lines. We need to find the width of the lead lines.
Okay. So we're given H, and that was 3.1 millimeters. So we use the design equation for the low impedance region, which is W over H is greater than or equal to 2. We said that was around 3, so we use W over H is equal to 2 over pi times all of this in a big parentheses, B minus 1 minus ln
Hold up, hold up, hold up, hold up. 2 over pi. Okay, you said B.
uh, 2 over pi, and then big parentheses, B minus 1,
Oh yeah, this is the ugly one.
yeah, minus ln, and then inside the ln is 2B minus 1, and then end of parentheses
Not to
for
be
the
confused with
ln,
beta.
yeah, and then so end of parentheses for the natural log, and then plus epsilon r minus 1 over 2 epsilon r, and then that is times the natural log or ln of b minus 1 again.
Hold up,
And
I'm moving something out of the way. There we go. Okay, so I'm still at epsilon r minus 1 over 2 epsilon r.
yeah, so it's that and then times, so just do another big parentheses, um, ln of b minus 1, and the parentheses for that plus 0.39, and then minus 0.61 over epsilon r, and then end big parentheses. And then to solve for b, we have b is equal to 120 pi squared over 2 z naught times the square root of epsilon r.
You said B equals 120 pi squared.
Yes, over
All of
2
that squared
120 times pi squared. Yeah.
over.
Or 2 times z naught times the square root of epsilon r. Actually, I
So
don't
for
know if it's all of it squared, because on the formula that I see, it's just 120 times pi squared.
oh,
So I think it's
okay.
just pi
See,
squared. Yeah, that's my bad.
that's what I was trying to clarify.
This is part of the reason why this class is so stressful, because you write like a paragraph long formula just to plug stuff into.
And then you get one number wrong, and then it throws everything off by a factor of 25,
Oh,
and there's a margin of error of 2%.
oh.
Still not as bad as playing Cuphead, though. I'll tell you that much. Still not as bad as
I
playing
believe it.
Cuphead.
I believe it.
5 hours. Y'all should check out that compilation, that montage. Put some banger edits in there. Okay, so I said I was solving this. Okay, so we know epsilon r is 1.7. So this is just 120 pi squared times 2 times 50 with the square root of 1.7. So then we just throw that in our handy dandy TI-84 hashtag not sponsored. It's gonna be hilarious if I get like sponsored by some tech company or something like that after my after my study streams.
Mhm.
You know, if y'all
Just
know
get
anybody at like y'all know anybody at like Apple or Google or TI or NVIDIA or something like that want to sponsor me, give your product an 800-star review. I promise. Dawn didn't even have to sponsor me. I'm just a huge supporter of Dawn dish soap. So we end up having our B value equals 9.08. So then we plug that into our massively long equation that nobody wants to ever do. But we're going to do it here live on the channel to show y'all exactly how long it takes. Whoever invented this formula, you deserve to be everywhere you deserve to be wherever you are right now. I'm gonna leave it at that. So you might have to help me out on this, Alex.
Yeah, I'm typing away in the calculator too.
So we have 8.1, or no, wait, you have 9.8. 9.8 Oh wait, no, you have 2 over pi. So 2 over pi times 9.8 minus 1 times natural log of I'm not gonna do the 2b stuff. I'm just gonna like write that as what it actually is. That shouldn't be 9.8, that should be 9.08. Sorry about that, y'all. 18.16 minus 1 plus 0.7 over 2.4. That's multiplied by natural log 9.08 minus 1 plus 0.39 minus 0.61 over 1.7. Long freaking problem. Now we can solve it. Yay! I hope I don't type this in wrong. Please, Lord, don't let me type this in the wrong way.
I gotta type. I got the answers already.
Okay, I'm gonna see if I get the same thing you get.
All right.
So I'm gonna do this in chunks so I don't make a huge mistake. So I'm gonna do 0.61 divided by 1.7, then do natural log of 9 point. Well, just gonna use the full value. Go back and grab it. 9.8 minus 1. That plus 0.39 is, yeah. Okay, cool. Okay, so everything in this big parentheses that I just solved for should be 2.12. And then you multiply that by 0.7 over 2.4. And that gives you 0.61 8 or 0.619. Oh yeah, by any chance, did you get the other helmet started?
Not yet. I will start it at some. I have something going right now, but I'll get it started after this is done.
Okay. I
Do,
just
do
don't
you
want to
want
like
do you want to see like the size of the other one?
yeah.
I'm gonna grab it.
Yo, Alex is a real homie. Uh he printed off a football helmet for me. It's absolutely huge.
It's huge.
I actually like I do really like it being that big, but I also know like it's gonna literally be a bucket on my head.
Yeah.
But hey, if you're not able to get the one before I leave for winter break, I'll take the big one. I'll make it work. I'll have a big bucket on my head. I mean, I'm a true
I,
Bengals fan. I'm a
you
true
know,
Bengals
if you wanted to do like some like parody videos or something with it, you can always just be like, what it's like being a little kid playing football.
fan. How toddlers play football. Okay, so we got that 0.619 that's being added to the natural log. So ln of 8. Oh wait, hold up. I can just pull this value from up here. By the way, this is something that y'all should practice. You younger fellas, use the exact value as long as you can. It will prevent rounding errors. I guarantee it. Trust me on that. Because rounding errors, you'll be like, I got the right answer, but it'll be off by point 0.3 or 0.03. And then it'll be wrong. So take it from an old man. Don't round too early. Okay, and then do this times minus this minus okay, so that then plus okay, and then multiply all that by 2 over pi. And I got excuse me. That's what I got for W over 8, 3.73. Is that what you got?
I got 3.61, but um yeah, I think it's close.
Well, that's a kind of big difference. Uh, what did you do?
I just had it all in one big formula. So after solving for B, which I got as 9.08357, I just did 2 over pi and then just saved the value of B to and plugged everything else in. Epsilon R is 1.7, right?
Yeah. It could be just that it's all in one formula and you may have just typed it in slightly wrong, but it comes out pretty close.
Yeah,
You
but
know
I mean,
calculators.
yeah, you just whatever value you get from that, you just multiply that from by h to find or solve for w. Because
So you multiply that whole thing by 0.0031 and you get W equals 11.6 millimeters. Wonderful, right?
yo,
Let's see. Let's see. We did a guide wavelength problem. Uh,
I think I'm gonna have to go here. I have to get some dinner in me. But
oh, you're good, man. Um, I think this was gonna be the last one because I know those guide wavelengths are also kind of new.
yeah,
I'm just making sure I didn't lose anything.
actually, well, I'll see you later.
All right, man. Take it
I
easy.
might be down to study tomorrow too after that 369 final.
Yeah, I gotta do that practice exam.
All right, well, take it easy.
All right, man. Have a good night. All right. So last thing that we're gonna work on is this guide wavelength thing. So we're gonna say the cutoff frequency for this item is 4.5 gigahertz. Um, basically, guide wavelengths come from guide wavelengths essentially come from waveguides, and it can it you're gonna call me crazy, but it can exceed the frequency or the not frequency, the velocity inside of a waveguide can sometimes exceed the speed of light. Um, so sometimes guide wavelengths are a little bit high. So in order to find the wavelength, so we need the frequency we're operating at, which is 8.2 gigahertz. So we do C over 8.2 gigahertz. That gives us our frequency, or that gives us our wavelength. I mean, I'm sorry. So we do that in our calculator, divide by 8.2 e to the ninth. That gives us a wavelength of 36.5 millimeters. And then our cutoff wavelength, or lambda c, is I believe that's the speed of light divided by the wavelength that we're given. So, or the cutoff wavelength, or cutoff frequency, not wavelength, cutoff frequency, divided by 4.5 e to the 9. And that equals 66.67 millimeters. So then lambda, the guide wavelength, you just do that. You do 1 over square root of 1 minus lambda over lambda c, all of that squared. So if you do this value divided by this value, and then you square it, 1 minus that value, and then you do 1, wait, no, then you do a square root of what the cheese? What did I just hit? You do square root of this 1 over that wave or guide wavelength is like 1.196 meters. So yeah, I think that's gonna do it for tonight. I hope y'all learned something. I hope y'all found it like kind of interesting. I know at least one person did. So shout out to Crimson. Thanks for tuning in. Um, Oh, okay, cool. SolidWorks. Oh yeah, I've heard of SolidWorks. Um, I'm sorry that I didn't read your chat messages. I was just like I don't have it set up on a dual screen. This is literally just my laptop. Um, but yeah, so I hope if you were tuned in, you learned something. If I did something wrong, tell me in the comment section. So I can study this before my test in 2 days. So yeah, big shout out to Alex. Appreciate him coming on here. Um, and with that being said, I want to say thank you guys so much for watching this stream. If you liked it, give the like button a nice slap to the face. Like an awesome person. I will see all you guys in like some regular videos and then another live stream like a week from now next time. All right. Catch y'all later.